Okay, finally, we got to talk a little bit about chemistry. And now we're going to look at the structure of amino acids. And you're going to find out that the structure of amino acids are very similar. There is only one kind of area of the molecule that begins to change, and this area is very important. We've got to kind of understand what groups go on in that area, but the foundation of an amino acid is all built with the same brick. That's it. So we're going to have to understand at least the three pieces of the brick that do not change. So we said that amino basically should stand for NH2, and that's what we're seeing here. NH2 that we can write, and I'm just going to write NH2 like normal. So there is an NH2 group that is involved in an amino acid. However, this will slightly get modified in a minute, and we'll explain why. But we do see an amine group involved in a amino acid. That makes sense. We also said that the acid probably typically refers to a carboxylic acid, and we do see that as well. So COOH group is on an amino acid because there is a carboxylic acid group that is involved, and that's what that means. These two things have to be connected. Now, before you connect them, I just kind of want you to take a look at the types of groups that these are. NH2 is a base, and a COOH group is an acid. So we are working with a acid and a base on the same molecule, and you know that something funny is going to happen when that begins to start taking shape. And we're going to take a look at what does exactly happen a little bit here in the next few minutes. So these two things are connected by a carbon. And this carbon actually has a hydrogen attached to it, and I'm going to put a random alkyl group down here at the bottom. So this is kind of your foundation for amino acids right here. So every time that you draw an amino acid, this is kind of what you need to draw in the beginning. Now, there's an issue here, and the issue is if we are talking about general structure, this might be okay. COOH and NH2, I don't really have to worry about has the acid lost a proton? Has the base gained the proton? Is there an interaction between them? I don't have to worry about that. But we are focused on the amino acids in our body. We're focused on the biological activity of these amino acids, meaning what do these things look like at a physiological pH? So there's the issue number one. So this is okay to start with. It's okay to kind of say, well, aminos in H2, acid represents carboxylic acid. This is kind of how we start, but we quickly change this structure over. And the reason that we change this structure over again is because this NH2 is a base and this COOH group is an acid. Now, acid-base chemistry never goes away. Acid-base chemistry, well, hopefully you memorize a little bit of it. You remember a little bit of it at least. And you will maybe pick up that a carboxylic acid has a pKa value and an NH2 has a pKa value. So hopefully you're not saying, well, what's pKa? I don't remember pKa, but if you are, then I've got news for you because we're getting ready to define it. So good. pKa is the acid dissociation constant. So acid dissociation constant. And this tells me the pH kind of when the acid or base loses the proton. Okay, so maybe I shouldn't really write base here because pKa specifically looks at the acids of those, and we need to figure out what are the pKa's of carboxylic acid and what's the pKa for the amino group. Okay, well, we can generalize this number. You can look up all of these amino acids that you want to look up. And you will be able to find pKa values that are associated with them. Exact numbers. But I don't want you to memorize exact numbers because they're all kind of close. And as long as they're close, then we're okay to generalize the whole family of amino acids. The pKa values of the carboxylic acids on most of these amino acids take place in the range of about a 2. Now, they will fluctuate. Some of them can go maybe to 1.9 or 1.8. Some of them can go up to 2.3 and 2.4. But they're around 2 on average. And that's what we can use for our purposes. The pKa of the carboxylic acids are around 2 on the amino acid groups. Okay, well, what about these NH2 groups? What about those? Okay, well, here's the funny story with the NH2 groups. The NH2 groups have pKa's, amine groups, have pKa's in the upwards of 40s, right? And these 40s make the NH2 group very basic. Well, pH of the blood, let's start there. pH of your physiological pH, at least, is on the range of about a 7.3 to 7.4. So you're slightly basic. Again, you're a little vat of stomach acid that walks around on 2 legs that has hydrochloric in it. And then the rest of your body is kind of a basic vessel that carries with it slightly basic blood. So on average, you're kind of basic. Nothing special about you. Alright, so 7.3 to 7.4. This is the pH at which all of these molecules are going to be exposed to. Well, if I look at pH of 7.3, 7.4, I look at my COOH group, and that COOH group has a pKa of 2. So that means at pH of 1, carboxylic acid keeps the hydrogen. Doesn't need to release it. At pH of 1.5, carboxylic acid keeps the hydrogen, doesn't release it. At pH of maybe 1.9, carboxylic acid keeps the hydrogen, doesn't release it. At pH of 2, however, we are getting over the pKa number of that acid. This is all review back from basic chemistry and back from the very first organic class that you've ever taken. So over a pH of 2, the carboxylic acid says, uh-oh, well, we're getting a little bit more basic in the environment, and I don't really like that, so I'm going to donate my proton and try to help out the situation here. And over a pH of 2, that carboxylic acid begins to release its proton. Hence, when I draw the real structures of amino acids at physiological pH, this COOH group has lost its acidic hydrogen, and I need to put a negative here to represent that. Again, the pKa value is 2. We're working on pH ranges of around 7. So 7 is higher than 2, which makes the carboxylic acid lose the proton. If you're uncomfortable with the definition of pKa's, I would suggest that you go into our playlist on the YouTube account and take a look at some of those lectures that concern acid-base chemistry for CTC 120. They are up there. You are more than welcome to click on that folder or click on that playlist and watch what you need. But that will go through a more explanation about pKa's and what these things do as far as pH and pKa is concerned. Now, NH2, however, this is a base, and bases we know love to be protonated, and this is a very strong base, and this is actually the pKa, or this is actually the structure of that amine group at physiological pH. We see an NH3 plus. This is a protonated amine, and protonated amines for amino acids have pKa's, we can say, of around 9.5. Now again, this is an average. Some of them you will see down into the 8.8s, some of them you will see up into the 10.5s, but this gives us a good average to kind of work with to determine what these functional groups are doing. So at physiological pH, we have a COO minus and a NH3 plus on these amino acid structures, and it's very important that that's the way that you draw them. So that is your foundation. That is where you will begin to draw all of these amino acids. We have a carbon in the center, and this carbon in the center has a NH3 plus and it has a COO minus, and it has a hydrogen. The reason that it's an NH3 plus and a COO minus is because we're regarding it in terms of physiological pH value. The environment that we put it in is very important to acid-base chemistry, and we're seeing that it's basic enough to make the acid lose the proton, but it's not basic enough to get the amino group to lose its proton. So that is the structure and the foundation that we will pick up on in the next video, and we will begin to describe what kind of amino acid structures begin to set them apart from each other. So in the next video, we'll follow up with this structure, we'll continue on with it, and we'll talk a little bit more about them. Stay tuned.